And the elemental analysis by OAS, optical atomic spectroscopy. This is using the optical spectroscopy for elemental or atom analysis. Atoms would transition between the ground state and excited state, accompanied quite often with the absorption or emission of radiation, which is quite often an light. So now we have atom ground state, Eg, and excited state, EE. And when a light, quite often visible light, comes into place, absorb light and the electron from a ground state would go to excited state. And your incoming light intensity would become, if it matches this frequency, the intensity would become a little bit weaker. Or the other way, it's already excited, or it can go back to the ground state. And in this process, it's going to emit a little bit of light and decay into the ground state. And in this process, the so-called characteristic frequency satisfies this relationship. H mu for frequency of the light, H mu, the photon energy equals to the difference in the energy gap between the ground state and the excited state. Absorbed or emitted light frequency are quite often atom specific. Different atom, depending on the different ground state and excited state, they have different characteristic light frequency. And for a standard with atom concentration CS, standard, C for concentration, S for standard, and if we shine a light onto it, the measured intensity is standard, I for intensity, S for standard. Then for an unknown sample, something that you don't know, and atomic concentration Cu, which means unknown, but you can measure the intensity, IU, and quite often we have this relationship. The ratio between C concentration and the ratio between light intensity is proportional to each other. Or if we know the standard, we can get, okay, if we have a standard, I know what's the concentration in my standard, then I can infer what's the concentration of a specific atom in the material. And what does it look like? For elemental analysis, OAS for quite often, some machine looks like this, okay? And the common procedure to do that quite often, you have to, we are talking about ceramics, we are handling solid material, but quite often these type of things, you have to dissolve the solid into a liquid. Quite often you have to use this using some acid, some HF, nasty acid, to digest the whole thing into liquid. Okay, and then so-called atomization, generate small droplets. Generate small droplet, you can use flame, very high temperature, or droplets to nanoparticle to vapor to essentially atoms. And then you can use plasma to do the same thing. And you can use the absorption spectroscopy, which means you shine light and you measure the light on the other side. Atomic absorption spectroscopy, shine light and measure spectroscopy, flame AAS, or you can measure emission. You do not shine light, you just flame, you just burn it and it will emit light and measure the emitted light intensity. And measure spectroscopy. For example, here shows different concentration of calcium within probably the liquid, and it shows, okay, certain light, certain wavelengths of light at a different intensity, and the intensity is related to the concentration. The frequency is related to the what types of atoms. And material scientists deal with this less, but chemistry department, they are expert in handling these. Okay. Other considerations. Typically, you can use liquid directly or solids to be dissolved, and detection limit down to ppm, parts per million by weight. Okay, and FIU, we do have it in the analytical center in chemistry department. We do have it. Elemental analysis via XRF, X-ray fluorescence spectroscopy. When high energy X-ray, you shoot X-ray onto the sample, it would knock out inner electrons. Okay, and the inner electron knocked out upon relaxation, which means the outer shell electron would go back to the inner shell. It would emit X-ray with energy that is lower than your incoming X-ray, termed fluorescent X-ray, and it's analyzed due to atomic specificity. So essentially, the right one is for your incoming high energy X-ray. It knocks electron away, okay, and outer shell electron would go back, and in this process emit so-called X-ray with lower energy. And in this process, we can measure the knocked off, the emitted X-ray. And quite often we have something like this. X-ray source shine onto the sample, measure the X-ray fluorescence using a detector and get a spectrum. Consideration, you can use bulk sample directly. In this case, you do not have to dissolve everything in water. Detection limit 10 ppm or higher. Okay. And if you study surface analysis, there are some other techniques that for material scientists or chemists, they quite often would use. We would quickly go through them one by one. The first one called OJ, electron spectroscopy. AES, OJ electron spectroscopy. It's a vacuum surface analysis technique. You are using a high energy electron and emitted particle. What you are collecting, you are measuring would be another electron, knocked out electron. Okay, and it can detect elements that are heavier than lithium. Okay, not very sensitive, 0.1%, not super sensitive, and depth analysis is detecting only the very thin surface layer, 2 nanometer, very thin. Spatial resolution, 20 nanometer or less or higher. The other one for surface analysis called XPS, X-ray photoelectron spectroscopy. These are just different techniques. Now you are using a powerful X-ray emitted to shine onto the sample, and now the X-ray will knock out the electron away. Okay, and you are collecting the photoelectron. Photoelectron is also used for analyzing elements heavier than lithium. Similar sensitivity. Okay, lateral resolution is not very sensitive, which means if I want a local composition, I cannot really tell one grain from another grain by this technique. I cannot really do local composition analysis. I can do depths, but not local, from one location to another location. The third one is so-called SIMS, secondary ion mass spectroscopy. We're using a charged ion, different helium, argon, ion, and spattered onto the material and knocking out the elements, the ions, and collect all those different ions. Anything heavier or including hydrogen can be analyzed. Extremely sensitive, down to ppb, parts per billion. Essentially, SIMS is too powerful. You can see anything with SIMS. Believe it or not, you can see almost anything with SIMS. That's its disadvantage, but the advantage is very sensitive. Okay, and depth of analysis 1 nanometer, spatial resolution from nanometer to